Okay, let's see. Let's start again. So the second lecture, again, will be more, again, technical subject about reinforced learning. So earlier, basically, I talked about deep Q network, basically how to train neural network to estimate Q value function. And the second lecture will be about what kind of other approaches are there other than basically learning neural network for Q value function. Okay, so let's reiterate it. It's just about an hour ago, so I don't think I need to recap too much, but I will briefly go over, right? So reinforced learning, again, was about having agent surrounded by the environment where it takes an action, and as a result, you get the reward and the state, in other words, observation. And again, one key difference from other supervised learning approach would be having this indirect feedback rather than direct feedback, right? And you can apply it to Mario, or we can apply it to locomotion, etc. And also, I talked about some of the, standard RL applications too, and as well as Markov property, where we have definition of state, action, and reward, and transition probability, as well as discount factor, right? And here, again, I would like to emphasize that this reward and discount factor is typically what humans define to train reinforced learning algorithm, right? And pi, action given state, is essentially tells which action you should take as agent. And our goal is to find this optimal policy which maximize the expected value of total reward, right? So our goal is to get the best reward, the highest reward of overall, given this discount factor, okay? And more formally, again, this is to maximize this expected total reward with given discount factor, gamma, and the reward design human-made, okay? And I will skip this part, okay? So there are many approaches for finding the best policy. This doesn't list everything either, but there are three standard or most popular approaches right now. And the first one we just talked about is what I just talked about in an earlier lecture, DQN, which is a value-based approach, where our goal is to learn this value function, Q value function specifically in this case, and we get this policy implicitly, right? Based on the value function, we get this policy, right? Whereas there's other approaches, but I guess I will probably skip, let's go over value-based DRL, which is what we just talked about. Our goal is simple, right? We want to basically function that measure how valuable is a state or state and action pair, right? And then we talked about all this thing. Once we have this Q value function, we can pick the next action based on whatever has highest value of Q, right? And then we talked about Bellman equation and some intuitions and etc. And I also mentioned that getting this exact Q value function is tricky sometimes because the state space can be huge and there's a memory issue, etc. Right? And that's why we approximate it, and then we use neural network for that, right? And that's basically what the first lecture was about overall, right? And now, not only just there's a value-based approach, there's a policy-based approach as well. So what I mean by that is, rather than just estimating value, we can directly estimate what action to take, right? So we don't actually try to value them, estimate the value, but we rather try to predict best policy at a time. Okay? The difference is, the first one was we evaluate each state or state and action pair, but now what our goal is to, given this is state or given this is state, what is the best action to take? We just directly predict it. In some sense, it's a little bit more like a classification. We can think of it that way, right? So in this case, unlike the previous one, rather than trying to evaluate or estimate the value of a state, right? Given a state, we just try to predict the probability, what will give the best outcome. What action will give the best outcome, right? So that you can compare these two things. So value-based is about evaluating value, Whereas a poly space, you don't care about the value. You only thing you care about is which action will give the best action. The basic probability of this action to give the best outcome. Does it make sense? It's in a standard setup. You can compare against a regression versus classification in a way. Assuming this action was discrete, right? So in regression, you try to evaluate how good each estimation is. Whereas in this case, we don't care about how good it is, but just care about which action is best. Does it make sense? Okay. So as simple as that, right? We have state, and we want to have this function f, trained based on neural network in this case, and that can predict this policy directly. Where what that means is, given a state, our goal is to predict this probability of what action is best one. Right? Yeah. So now suppose we have a grid world. It has nothing to do with LOL, by the way, for those who are excited about LOL. So there's an agent, and there are some states you want to avoid. This is more like a maze, okay? And once we have a maze, there are some states to avoid, as there are some state you want to get to, right? And and you have action of up, down, left, right, okay? And there's a feature where there's wall, or there's move to right, and so on. And when you have this optimal deterministic policy, you can do this. The value, so if you train an agent based on value-based approach, the problem is sometimes some states has equally important state, then it can get stuck. So you see, when you train if you train a value-based approach, in the gray one, so between these two, what will happen? So here you will move to right, and here you will move to left. Because what will value function do? You just have which state has a higher value, which action is the best value, and it just takes that as granted, right? Whereas in the policy-based approach, it will try to give you a probability. Moving to left is how good it is. How likely moving to left is the best one, and how likely is moving to right is the best one. And based on that, you can sample. So you can actually have a stochastic transition here. So in this case, now you can have equal probability to move to left and equal probability to move to right. So that's one of the key difference when you train an agent from policy-based approach and value-based approach too. Okay. So in other words, policy-based approach is nice because Q function is difficult sometimes to train with high dimensional or continuous action space, right? And also when you need a stochastic policies, for example, just like this one. So if it's a deterministic, the problem is you will just keep moving to left and right, and you will get stuck in between this, right? You will move to right and move to left because of the non-stochastic property here. Whereas in the policy gradient, a policy-based approach, you will have some probability to move to left and some probability to move to right. So even if you actually move to left, you will come back and you will move to right based on sampling. Okay? So that's one of the advantage of training policy-based approach. So policy-based RL can solve this. So again, let's show this. Okay? Let's suppose, let's just compare again value-based approach and policy-based approach. Okay? In a Q value, so after you train a Q value function, so let's suppose you have 7, 7, 8. Okay? So what will you do? So suppose you're playing rock, scissors, paper here, right? So what will be your next action now in this setup? Okay, hopefully this is clear to you now. Okay, so what will be the next action? Right. Yeah, so it will be next action because the highest value is on the rock here, so it will play a rock, right? And what will be the next one again then? It will be rock again, right? It will keep doing rock and rock and rock. right? And because there's no stochastic component here. And then there's no, and this, while there's a Q value, the nature of, if you think about the first lecture, for those who remember the equations and all that, there's, even the value is 778, it has nothing to do with the probability at all. It doesn't have a probabilistic representation here. So it doesn't mean you can sample just a 8 out of 7 plus 8, right? It's not 8 out of 22. You don't have this representation anymore. So you cannot just randomly sample. Does it make sense? So because of that, it will keep playing rock. Or even if you try to sample it, there's no representation. It doesn't have a real meaning in it. So you cannot really just sample simply based on this Q value. So you're kind of stuck. Whereas if you do policy-based approach, only thing you know for now is that this is a probabilistic representation. You don't have to know how to train it. But suppose you have 0.33, 0.33, and 0.34. But because now this has a probabilistic meaning in it, you can sample it. So 34% of time you will play rock, but 33% and another 33% you will play paper and scissors respectively. So do you see the advantage of it now? Okay, so that's one advantage. So Q value doesn't have this probabilistic representation, so you can get stuck sometimes. Whereas a policy-based approach, you can have this probabilistic meaning where you can sample. And it can be advantageous in a stochastic setup like this. Okay? So let's take a look at what the policy-based approach now is. So again, our goal is finding this optimal policy still. It's the same goal. Again, our goal is to find this best policy that can maximize expected return. Our goal doesn't change, right? So in this case, our goal is to find this parameter theta, which estimate the value of the return reward, total reward. Okay, this is again total reward, same equation from earlier, right? Based on the theta, neural network parameters, and our goal is to find the best parameter that will give you best reward. Right? And we will solve this by gradient ascent, just like any other deep learning algorithms. Okay? And before going into some of the mathematical details, so let's take a look at supervised learning here. So you have a given image, you have a neural network here, right? And when you do forward pass of a neural network, you will have some probability in supervised learning setup, simple supervised learning, right? And once you have log probabilities, you have a loss function, which is based on ground truth. And you get the gradient back, and then you do backward pass, and you update the parameters, and you again go through the forward pass, and then we'll go back and forth, right? And this is under supervised learning. But the problem, again, when you apply it to reinforced learning, the problem is, what is the problem? What is the problem? No problem? The problem is we don't have ground truth, okay, in a supervised learning setup. In a reinforced learning setup, we don't have ground truth to compute a loss function, and that's an issue here. So in a reinforced learning setup, we have a forward pass, and we compute some probabilities here, and then we sample an action based on this probability, and then we compute a loss function based on it, and then based on this sample action, we get the reward, and based on the reward, we compute a gradient, and then we update the reward. We do backward pass and update the parameters. Okay? So it's a sampling-based approach. So once you have probability, estimated probability, we take some actions, and then we get the outcome of it, and we update the policy based on the parameters based on the outcome of the reward. Okay, that's a key difference. And in fact, in terms of higher-level idea of policy-based approach, this is all you need to know. So you just get some reward based on some current estimation of policy, and then you update to you get the gradient, you compute the gradient, and then you update the parameters, and you reiterate it over and over. And that's all it is. The tricky part is how to compute a gradient based on reward. And we will talk about it a little bit more now. Okay? But I think some of the things you need to bring home is that in the supervised learning, you get the direct supervision to compute a loss function. And in this case, you don't. So you basically take actions to get this reward and compute a gradient based on this reward, returned reward, and keep doing it. And for those who are familiar with reinforced learning or policy-based approach, this part basically creates an issue or hard part of training reinforced learning, especially when you have sparsity word. The issue is if you're under sparsity word, when you take action based on this probability, okay, it's for more advanced students essentially. But for those who, when you take an action, you may actually not get any reward because the reward is very sparse. And then if you get sparse reward, you get no reward, which means any action you took has equally same value, right? Even if you die, even if you succeed, it doesn't matter. Basically, you will get all 0 reward because the rewards are really sparse. You actually don't get even to the state that you get the reward at all. Then you basically keep updating with a 0 gradient, which means your parameters doesn't go up at all. And then the more sparse it is, your network will likely get no update forever, and you don't learn anything. And that's one of the reasons sparsity word is a hard problem. Okay? So let's take a look again here. So policy gradient. So how do we do? So this approach is called the policy gradient approach. And how do we do this? I mean, again, at a high level, it's very intuitive. So you run a policy for several episodes, which means based on current neural network, again here, you compute basically based on whatever network you have, you compute this policy estimator, okay? Remember in the Roxisa paper, you get some probability of each action, right? 0.33, 0.33, and 0.34. You get that action, that current policy function, and you just act based on that current function multiple times. And that's what it means by episode. Several episodes means multiple times, okay? And then we take a look at what actions led to the higher reward and what we'll like to do. If you get better reward, you want to increase that probability. If you get worse reward, that means you want to decrease that probability, right? So here, suppose you have one policy. So with the current policy, let's say you went up, down, up, down, 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 up, and you win. So you get the reward, win. And then you go down, up, down, up, and then you lose, and so on. So then which one do you want to increase probability? Obviously, the first one and the fourth one, right? Because you win, right? And then second and third one, you want to decrease the chance of it happening, right? And that's all you do, again, right? At the abstract level, very simple. Okay, and that's basically increasing the higher rewarded one, and then decreasing the lower reward one is called policy gradient. It's just gradient descent, right? Right. So more formally, again, remember this equation, which is expected return of total reward of the current parameter of Z, and given the trajectory, so you created this trajectory by sampling, basically one sample of, so for example, up, down, 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 up. That's one trajectory, okay? So each trajectory means just one episode here is one trajectory, okay? It's a new terminology. So each case it went to win or lose, that's basically one trajectory it's on. So you have some trajectory that has finished, okay? And based on this, you can compute all this, and I can walk through a little bit here, but this is just a simple algebra here, right? I span out the expected term here. So here's the expected term here, right, of the total reward, and then it's just an algebra of rewriting the expected term, right? And once you have the expected term, there's a gradient. So you basically put into the gradient here. So again, this is a simple, everything here is just an algebra, some swapping and all that, right? So first, expected term. When you put the gradient into probability here, because it doesn't have, this reward doesn't depend on theta at all. You can ignore it. And then go to the third step, which again, this is just a simple algebra from gradient component. So you can actually span out here. And it's like the same thing here as well. But you can ignore all this steps. It's not as important. But the only thing you want to probably remember is this, the total reward, gradient of total reward goes down to all the way here, where the reward is independent of the gradient here. And there's a log term here. Okay? It's just follow this simple algebra rules. Okay? But why is it important? Then based on this, because we can compute policy gradient by sampling. Right? Because we cannot directly compute this policy gradient, probability gradient, because this depends on, this P depends on theta. You cannot directly compute this. It's hard. But where we can sample and compute this, okay? And that's the key idea, right? And if you think about it comparing to the normal gradient descent, you can think about the reward is it acts like a learning step, and the inside is like a gradient direction, score function. It's just an analogy. Okay? And this part may not be as important, but so you have this is score function, and after parameter update, it gets to the desired state. But you can ignore this slide. It's not as important. Okay. So how do we do this in an algorithm matter? So this part was just more, this part was more mathematical definition or derivation. But how do we actually really update this? Is called reinforced algorithm, okay? Which is Monte Carlo policy gradient. How many? Are you guys all familiar with sampling method here? Electrical engineering student, maybe, I guess, or CS student. Have you heard of sampling before? Or is it all familiar? You don't have to know anything detail, okay? It's a very simple concept. So the problem is with the gradient is sometimes, you probably are all familiar with calculus here, right? The problem is sometimes it's very hard to compute gradient directly from the function. Because sometimes function is just a black box, so you don't even know the function at all. And even when you have a function, it's very hard to compute it analytically, right? So then what do? You just sample some values, like a Newtonian method, and then you just compute a gradient. You estimate the gradient based on sampled output. That's what it means by sampling, okay? So in other words, it's a simple trick to compute a value that's hard to analytically compute, okay? So what do? So you generate samples. In this case, basically run some of the policies. So you already have some estimator, right? Deep learning estimator of what policy what is the current policy, right? And based on current policy of this estimator, you run this function, then you will get some trajectories, like the one I showed you, up, down, and so on, based on current policy, right? Which may not be optimal. That's okay. It's basically whatever you have. And then based on this, whatever you have, you sample some trajectories, and you sometimes get win, and you sometimes get lose, and you get the reward, right? So basically generate some samples, and then fit a model estimating the return. So basically get a reward based on it. And then improve the policy by updating the parameters, basically meaning doing gradient, and then go back. So after you do gradient descent or ascent, depending on how you think about it, you will get some updated policy function, estimating function, and then you sample it again, you get another reward and a gradient, and then you keep repeating it. Okay? That's a basically sampling-based approach. All right? So again, same thing here. So you have reward, expected reward, rewritten in a different form. That's the same. And our goal is to compute this gradient. Right? Any question? Getting tired? I'm tired too. So yeah, the third lecture will be a little bit more entertaining, I hope. It's a little less mathy, I guess. Okay. So yeah. Any question? No question? Are you guys all following, more or less? Don't be shy. Yes?
For each iteration, the P will be updated.
Can you say?
So for each iteration, the P function will be updated.
So the J will get updated. J is an estimator of policy or expected return with theta. Theta is the parameters, the neural network parameters, which estimates total reward of each state or state and action pair, depending how you think about it.
Okay, thank you.
So each iteration, so basically what you want to do, so when you do policy gradient, right, or any gradient, so suppose that this is our estimator J function, right? Our goal is to update this function. You want to make this estimator as best as possible, because this will give you the best approximator of the total reward. Does it make sense? Does it make sense? Wow, I have no idea whether it makes sense or not to you guys now. I see. Some reaction. Give me some reaction. Does it make sense? Yes? No? So, okay. Does it make sense to everyone? Or does it make sense to anyone? I see. I need to learn how to read Taiwanese now. Okay. Don't worry, I'm a Korean, and Korean students are pretty same too. It's a very subtle, I think. But in US, people are much more reaction. They have more reactions in it all. So, okay. Yeah. So I will just explain one more time because I guess not everyone said it's clear. So this J in this case is about the total reward, estimating total reward of any state, any given state. Okay? And theta here is just a neural network parameter. Okay? So because you want to, and then what is our goal again? As long as we can estimate which state or which state and action will give the best reward, our problem is solved because we can just follow it, or we can just follow the probability of that, right? Is it true?
Yeah.
Okay. And to update this function, what do we do in general? Once we have whatever value function or estimator function, we update by gradient descent, right? That's a typical approach. And to do that, basically we compute the gradient of J respect to this parameter theta.
Excuse me.
Yes?
What does the tau stands for?
Oh, what is it again?
What does the tau stands for?
What does tau stand for here? You can think of it, I think, in this case, state. Yeah, or sometimes you can think of it as state and action. Depending on, this tau can be as state or state and action. Yeah.
So we sample the different kind of the state
exactly.
path and computed the gradient.
Yeah, for all the future, yes.
Okay.
Okay? Yes.
Then if we can only get the reward in the end of the game, then most of the R of tau will be 0, right?
Oh, can you say it again? Sorry.
If we can only get the reward in the end of game,
Right.
then the R of tau will be, most of them are zeros.
That's right.
Okay.
Yes. Yeah. Okay. But I mean, because you're summing up everything over every entire trajectory, you will get some reward, assuming you get some reward at the end of the day. Okay. So anyway, how far did that go? Okay. So we have J, again, which is estimator, and our goal is to get the best estimator. And for that, we do gradient descent. And to do that, we compute a gradient of J. That's a simple, right? And the way this form is just an algebraic form of breaking it, just putting the gradient into this this integral. Because R doesn't depend on the theta, so you can just put into this probability here. Okay? All right. So if you look at this gradient again, as I said, this is because J theta gradient is intractable, because P depends on theta again. We just have to expand it out a little bit more. So this again is algebraic trick. Okay, gradient of this probability just becomes probability gradient of log probability. If you can go home and follow the trick here, okay? And then we can substitute it back to here, right? Then we get this gradient of J, which is equal to expected value of R gradient of log probability of a P. Log of a P, yeah. Okay. Everything here so far is just a simple algebra trick again, right? But we write in a different form because it actually has some meaningful interpretation later for us. In this case, for example, this can be estimated with Monte Carlo sampling. The name is pretty fancy, but really it means is we sample stuff. We sample multiple iterations, and then we update the value. We estimate the value based on sampled result. Okay? So especially this one. And that's what the reinforcement algorithm is about. So the first case is, the issue is sometimes we don't, the problem is, again, as I said, the problem is this P may not be known to us. The transition probability is not known to us. It's a black box function. So we don't even know how to interpret this one. So that's why we actually are doing this sampling here. So for example, because we don't know this transition probability, we convert it to, again, this following some algebra here, we can convert it to this one, and then we can differentiate it. And eventually we get this function, okay, which does not depend on transition probability anymore. So all you have to remember in this case, again, is that with some algebra tricks, we can go home and read a slide or the paper. You get to the state where the final equation does not depend anymore on this transition probability, which is unknown oftentimes. Right? So transition function, again, is the chance of you, when you try to move to left, how likely you will get to left or you will not get to left. That's basically a transition function. But this kind of information is often unknown. Right? When I jump, what's the likelihood of, what's the probability I will fall down? I mean, I don't know. It's hard to estimate sometimes. Or sometimes you just don't know until you try it many times. But how do you estimate it? You just jump many times and then you can estimate it. I mean, right? You don't know how many times you will fall down. In the real, let's suppose that, the God created world. I don't believe God, but let's suppose that's the case here. Then there's a certain probability you will fall down when you jump. But you don't know that number, really, right? You don't know the real number there. But one way to estimate it is you just have to jump 1,000 times and count how many times you fall down. And that's sampling-based estimation. Right? And that's the same thing. Right? So now this part is not anymore depending on transition probability, which we don't know. And that's why we can use this form, which is all derived by some algebra. And we can get to this form. And now finally, we can do sampling-based approach to get the gradient of J, total reward estimator. Okay? And this is just rewritten in algorithm form for computer science folks, okay, from the paper. But again, it's the same thing. We just sample multiple trajectories and compute a gradient, and you update a policy. You update the estimator based on this gradient, and you sample again. You get this gradient again, and go on and on and on. Okay. All right. So that's a reinforced algorithm. Okay. So now let's go back to this one. Remember, I showed you earlier, this is, again, just a rewritten form of this gradient of J estimator, right? And the first term here is, I said it's a reword, but which is acting like a learning step. And the second term is a gradient direction in a gradient descent form. So obviously, what will happen? If the reward is high, what will happen? You will move toward the gradient direction more. If the reward is small, you will move little, right? So it follows our intuition, right? When you get high reward, you move toward the gradient direction. When you have smaller reward, you will move less. And if you have negative, you will move to opposite direction, right? Any issue with this? It's not a fundamental issue, but I guess it's just with people who have experience with reinforced learning a little bit. Yes?
When we do a gradient descent, we have a learning rate. So what's the learning step?
Oh, can you say it again?
When we do the gradient descent, we have a learning rate for...
Learning rate, yeah. We can have a learning rate here too, but we don't include it here for the simplicity.
Okay.
But yeah, this type, I don't mean that the reward is not really learning step here, but it's just acting like a learning step. It's conceptually, you can think that way. How much you move toward the gradient is what I want to show here. I think the issue with this is a little bit hard. I mean, it's a little hard question. I mean, I don't think I know the answer myself if I was asked. The issue is in reinforced learning, the reward in general, return reward has a high variance, okay? Even with a very similar trajectories. So in other words, this reward can have a very high variance, and that makes training very tricky. So you want to make this learning step, even though the strict derivation of this J, gradient J, is basically this form, we perturb it a little bit, the definition. Not the definition, we just perturb this equation a little bit by interpreting this in this way. Okay? So again, when you follow this algebra, this is basically kind of simple derivation you eventually get. But by interpreting it as if this is a simple gradient descent, we perturb it just following a simple gradient descent. Which means, for example, you change the internal term of this total reward so that we can reduce the variance of this term. Because if you have this high variance here, it's really hard to train. Because it will keep jumping around, just like it's standard neural network. So you want to reduce this variance issue. And for this, you basically have you have different way of doing this. It's a simple like a tricks, in other words. So basically accumulate reward rather than using just a single reward, or sometimes you have this discount factor for reward, so that you actually try to minimize this variance of different trajectories. Okay. And also there are different ways of doing this. So this is all sort of different techniques or simple tricks to make this a high variance issue go away. Okay? So you now even have this baseline here to reduce the variance as well. So these are all these things it come out when you want to train the even standard neural networks by putting some discount factor or baselines and so on. Okay? This is less important. Yeah. And also, yeah. And for choosing this a good baseline, one other way of using baseline is actually by putting expected value of that state. Okay. So you can actually reduce, just like, just using this value function we trained earlier, and use that value function to reduce this baseline is one other approach too. Okay. So now, if it's too different from value function, then it will be large. If it's close enough, then you don't actually update it as much. All right. So that was for policy-based approach. Any question about policy-based approach? No question? Okay. So we can move on to the third topic of reinforced learning. So we talked about value-based approach and then policy-based approach, right? And then the other model is now actor-critic model. This is probably the most standard model being used out there right now. I mean, there's many different variations of actor-critic models, but in terms of conceptually, this is what people often use now for most reinforced learning in these days. Okay? So actor-critic is basically simple. It's a hybrid model. So you have a value-based approach and you have a policy-based approach. What do? You try to use both ideas now. And that's the basic actor-critic. Okay? So let's take a look what the motivation here a little bit. So for policy-based approach episode, so basically each round you have to go all the way to the end to get a trajectory, right? So you have to go move up and down and so on, so until you get to some reward, like, or basically the game has ended, right? And that's basically what this equation. So this is a way to compute this equation and so on, but data can be inefficient many times, right? Because it's really hard to keep running forever, right? But this, as earlier I mentioned that you can use this value function to estimate this reward. Instead, for example, to reduce the variance, you can also use this evaluated estimation, and that's basically the basic idea of actor-critic model. So how can we learn Q and value functions, okay, while also train this policy gradient method is the basic idea. So actor means here policy, and critic means Q function. All right? So that's why we call it actor-critic, meaning policy and Q value estimating function together. So actor just tell you which action to take. Critic tells you how good action was and how to adjust, right? It's a simple concept at a high level again. And then you compute this advantage function, what we call as advantage function, which is Q value minus value function, by how much of an action is better than expected. And you can interpret it also reduce the variance of policy gradient too. Okay. And this is we call it A2C algorithm because it's advantage function based actor-critic model. And there's also A3C as well, but we are not going to discuss A3C today. So remember, it's basically based on earlier policy-based approach equation. So the later part is the same. Basically, there's a gradient of the log probability. And the earlier part, which is substituting this reward, we substitute to Q minus value. It's the same. It's basically what you call it as there are different ways of interpreting it, and this is one way of interpreting it now. And the algorithm is simple as that too. So you initialize parameters, and you compute this advantage function by sampling, and you update a gradient, and you repeat it. And you update, and then you update a Q, and then you repeat it again. Okay? And this, again, is one of the most standard approach now, combining two different worlds. Okay. All right. Any question about the critic model? Yes? I cannot hear you well, actually.
Okay, so in the
Yeah.
algorithm, there is alpha and beta.
Yes. Yeah, it's a parameter. It's just this, it's like a learning rate. Yeah. Any other question? If not, we are pretty much done for algorithmic part of reinforcement learning I want to discuss. But before moving on, no more question? We can go back to any other topic too, but I just want to make sure everything is clear so far, or at least most part of it.
Could you please go back maybe two slides?
More?
One more?
Yeah.
So I remember there is something minus something, and they say you say it's large or small.
Oh, I see,
So,
I see.
Yeah. So how would you define it's a large or it's small?
No, I mean, it's just if it's a relatively large or relatively small. It doesn't have a, it's not like a threshold based. It's just when you interpret it, when it's large, it's going to do this, and when it's small, it's doing this. It's interpretation rather than any actual thresholding.
Thank you.
I mean, for those who are beginners to reinforcement learning or deep learning in general, you can just remember this part. I guess there's a value-based approach, and there is a policy-based approach, and there's actor-critic model, right? And value-based approach directly try to, it's actually trying to learn or estimate this value of each state or state and action. And there is a caveat of it, which is sometimes it's hard to interpret what it means. So when you take an action, you cannot really sample, like a rock, scissors, paper example. And there's a policy-based approach where rather than trying to estimate the value, you actually directly trying to compute a probability of what action is going to lead to the best outcome. And that's what the policy-based approach is about. And lastly, actor-critic model tries to combine idea from both approaches. And it doesn't really have a mathematical interpretation as much, but there is in practice, this works the best so far as well. But I mean, and then after people try to interpret it in a different way, for example, I showed you, this learning rate, and there's a score function, and that's how people interpret it more of the actor-critic model later on. Okay. Okay. Yes.
So we define the advantage function in order to replace the old reward function. Do we do this to cost down the variance?
What was your question?
We use the advantage function
Right.
to substitute the original reward function.
Yes. Okay.
And we did this to cost down the variance of the sparse reward.
Right, exactly.
Okay.
I mean, we don't, yeah, it's more of an afterward interpretation, let's put it that way. So instead of, so earlier, when you directly derive it, this part is reward, which is just really, we interpret it as it's just a way of deciding how much you move toward the gradient, okay? I think I showed a slide very earlier. Where is it? So this is like after you derive it algebraically, you realize this is what actually happens. And it often fails or often is unfair. We realize it's probably because this reward function is fluctuating a lot. And that's when we realize this part term, the reward doesn't have to be exactly staying this way. And we can substitute it because this is just a really, I mean, in our interpretation, this is more like just a learning step in a gradient descent. So rather than using reward, we are trying to use different form. And that's one way of using, which is coming down to this Q minus V.
So when doing actions by the actor, we actually update the V and Q first, and then we update the gradient.
Yeah, we update
using
everything
them.
all together.
Okay.
Yeah. Nope. Any other question?
So basically
Yes.
you're trying to update.
So basically, you was trying to update these two things, like the theta and also the phi altogether, right?
Yeah.
And I suppose it would be highly depends on the initial point.
Yes. Yes. It's just like any other learning algorithm. Yes. Yeah. It depends on the initial value and also a lot of parameters in between too. But that's yes, it's a caveat of this algorithm, but it's also a caveat of any, I guess, deep learning based approach right now. So, yeah.
So basically, most of the time you will try to run this multiple times and then
yes. So yeah, that's one of issue in reinforced learning. I mean, in deep learning earlier era, I'm talking about like 2010 or 11. The issue was that initial value or parameters was very important. In other words, it was very sensitive to all these initializations. And I think people found different way of, initializing it and all that now, and it works reasonably stably compared to at least before. But I think in reinforced learning right now is at a similar state of 2011 in, just a standard, I guess, deep architecture, which is it still suffer a lot based on initialization. So if you run the same algorithm, basically on the same environment, which is a basically non-stochastic environment, but the result sometimes can be very different too. So in a research, the problem is that when we submit a paper, we can run once and you can get really great result, but when you run a second time, it can be very bad. So now in the reviews, people often ask for multiple iterations at least to estimate how good is your algorithm, basically. Yeah. Because one iteration can really solve the problem sometime, but second iteration, it can completely fail too. It can go from like heaven to hell, literally, right now. Okay. Any other question about algorithmic part of reinforced learning so far? I guess this lecture might end earlier than I expected, but I have a few more slides, but I think it's still going to end a little earlier. Yes?
I want to make sure my understanding is correct. So
Sure.
For the policy gradient, we instead of knowing the true gradient of policy, we sample it again and again and estimate the gradient of policy, right?
Right.
Okay.
Right. Yeah, it's just basically sampling-based gradient approach. That's what I really meant in a longer version. Yeah. All right. Is that all you have in terms of questions? All right. So let's discuss a little bit of the challenges of reinforced learning. I think I wrote this down a while ago, so I don't know how much of it still holds true, but I'm assuming the problem is still the same. Okay. So I already talked about most of the challenges I will discuss here. So do you guys remember? Or do you have any thoughts on what is a challenge? Or what would be the challenge? I think most of it is we already discussed it now. What is it again?
Markov chain assumption.
Oh, Markov decision. Yeah. So there's this Markov decision process assumption, which is true still. Markov property essentially. Yeah. I don't think people consider it as a challenge. We just take it as granted at this point, I think, rather than to think of it as a challenge. But yeah, I think that's definitely an issue. And anything else? Anything else I mentioned or anything else you think of? Yes?
How to decrease the number of iterations required to train it? How to decrease the number of iterations required to actually train a network using reinforcement learning?
Exactly, number of iterations. And this is a particularly problem for reinforced learning, because reinforced learning really is our initial motivation. Where do you think it came from? It's coming from robotics. It's not to solve the games, really, right? I mean, really, the reinforced learning was motivated based on robotics problems. And the issue is if you have to train, a million iterations. In supervised learning, it doesn't matter, right? You just train a million iteration. For image classification, you can train for 2 weeks, it's fine. Or even 2 years, it's okay. You've trained once and that's it, right? But the problem in reinforced learning is one, if you're training for a million iterations, one, it won't even end in 2 years. If you can end in 2 years, that's probably fine. I mean, but the problem is you cannot do it. And physically, it's probably going to run down the robot. If you run the same algorithm for million iterations in one robot, it will probably break down. And the other issue is there's a safety issue and all that we talked about too. So we need to reduce the number of iterations. And this is a much more sensitive issue for RL. And especially for deep RL, it's even worse right now. And what is it again?
Initial is a
yes,
very sensitive.
It's sensitive to many parameters.
So
yes.
maybe reproduce some tasks. We
right.
need some same redundancy.
Yeah, reproducibility. Yes. Yeah, that's one other issue. Anything else? I wrote down 4, and one of them wasn't mentioned so far. I don't mean that there are only 4 problems. There are a lot of problems, and many of them are what you discussed too.
So how much your learning can export the state space?
What is it again?
How much the state space can be explored by your learning algorithm?
Oh yeah, exploration issue. Yes, that's something I didn't write. I think, but also it's a very hot topic right now in current research. Number of exploration space is too big in general for RL, right? You can imagine if you want to train a human, for example, like a robot like a human, in a standard reinforcement learning approach, you will have to exploit it to the real world. And the problem is there's such huge space. It's related to the number of iterations too, but at the end of the day, there's just huge space to learn from. And it's hard to explore all of them. And especially when you have zero idea, at least when humans are born, we have a brain which is inherited from our parents. So even in the beginning, we have some vague idea about the world, right? It's encoded in our brain, or at least I do think so. And we can quickly get idea, but the problem is in RL, even after a million iterations, oftentimes you don't have any idea about the world. And with a random move, it's very unlikely you get to any point. If you suppose with a random move, with my random move, how likely will I ever touch that Coke can on that table? It's probably almost 0, right? I will probably go out the door and then will never come back to this room even, right? So that's the issue, and we call it exploration issue. And there are a lot of work trying to reduce this issue, and for example, intuitive learning. And how do we learn from other agents? And or imitation learning. So some of this will be talked today in the 3rd lecture, but that's another issue. Okay, anything else? Yes?
It's hard to find a really meaningful reward function. It's really hard to find a really meaningful reward function.
Yeah. Okay. Reward engineering. Yes. So it's hard to design a right reward for right model. It's really easy to design a very sparse reward, but when you try to design something more meaningful than just a sparse reward, it's pretty tricky. Maybe I should stand over there. Then maybe people over there will talk more. Okay. Wait. So yeah. All right. I think any more suggestion or any more thoughts? I have one more, but I think that's basically it. I can talk about it too. Okay. Oh, yes.
The difference between simulation and the real world.
Oh, I cannot hear you well.
The difference between simulation and the real world, because we can know everything in simulation, but in the real world we cannot know everything.
Right. Yeah, that's a little more related to how we can solve the gap between. Yes, but that's also a good answer too. Yeah, sure.
And the risk, because try and error is is work in simulation, but we cannot let a job learn the action and
right, yeah, sure. Yes.
In general, a model trained to solve one game, for example, can't solve another game without being retrained.
Oh yeah, that's a good answer. Yes, it wasn't listed here, but I think that's also a very good answer. So generalization of reinforced learning, meaning once you train in one environment, it's pretty much practically unusable in other environment. Whereas humans, for example, once you played two, three different games, once you're pretty good at 2, 3 different games, when you are given the new game, we can play pretty well. We can generalize pretty well. And when I can play good sports and stuff, if I can play a few sports pretty well, when I learn a new sport, I will be pretty good already compared to someone who is a complete beginner, right? But that's not as true in RL. Although there are obviously many ongoing work trying to solve this generalization issue, but I don't think there is one standard method I can name that will solve the problem. Okay? But generalization is a well-known issue of any learning algorithm in general, but also in RL it's also true as well. Okay? All right. If there's no more, I will also talk about what I meant here. So I think all this thing came up except the last one. So number of iteration, we talked about it, and reward sparsity. If the more reward is sparse, it's harder to train, and there's a reward imbalance or this engineering issue. And the last one is a hierarchical nature of the task. So many tasks in the real world, it has a hierarchical structure. And what this really means is the complexity of the space you need to explore is really, really large, right? So if you think about it, like many tasks, you first have to achieve one thing to get to the second game. So let's suppose my goal to learn, so suppose I'm here now as a human, even as a human, right? Suppose the game, no one told me about the game so far right now, but maybe the game was to grab this Coke and bring it to the another office, right? The issue is even getting to my another office is already probably hard by random exploration. So if you didn't tell me anything, if you didn't give any clue about it right now, what is the chance for me to randomly explore and grabbing this Coke and move to the other office? Even grabbing Coke is hard, and even just going directly to another office is already hard too. That chance is already probably 1 out of a billion or even less than that. But now you're multiplying these two things, 1 out of a billion times 1 out of a billion. And if this task is about going to Coke and open the Coke and giving to some other person, then it's like, obviously you can imagine this is a huge exponential issue. And then suppose you're going to give me the reward only when I actually successfully open it and give it to that person. And then the chance of me hitting there is probably, I'm assuming it's worse than the number of atoms in the real universe right now. And it will never happen, which means it will never happen by random exploration. And that's assuming I know how to even grab a Coke, right? So if I'm a robot right now, I don't even know how to grab a Coke actually to begin with. So it's just a huge exponential issue, and that's basically hierarchical nature of task, and that makes it learning practically almost impossible as of now. Okay. So, but obviously there are many ongoing works trying to address some of these issues. So, for example, for reward sparsity, when you have a very sparse reward, this work is by Berkeley, and which is called intrinsic motivation. You don't have to understand this diagram. I just put it as as a figure for fun. But for intrinsic motivation, really the goal is that we are assuming, machine also has some motivation intrinsically encoded, and based on that motivation, we train a network, and so you already have some idea about the world, just like a human again, right? When I bring you to the new world, you're not going to just randomly bang your head to the wall, right? It's unlikely you will do that, right? So we have a really good idea of what you want to do, what you don't want to do. You have some idea of what you would like to do, and that's basically a high-level idea of this paper, and that's one way to solve or address this issue. Okay, and again, hierarchical nature, as I said. So what is the chance of you actually successfully make a breakfast when I didn't even tell you about what to do? Almost a 0, right? And And there are many ongoing research on solving this hierarchical nature by trying to break it down to task into multiple self-tasks and learn each self-task independently as well. But again, this all again require quite a bit of reward designing as well too, okay, in general. All right? Okay, and I think that basically concludes pretty much the algorithmic part of reinforced learning today. I guess we ended 25 minutes early. So if you have more questions, I can talk about it. But this is basically what we discussed today. I think some key things to remember is just reinforced learning is a way to learn from indirect feedback. And we talked about Q-learning, Polish gradient, and each has its own challenge. And to address it, we combine it to actor-critic model. And there are a few more variations of this, but if you understand this is three method, Q-learning, Polish gradient, actor-critic model, pretty much everything else is just a simple or some variation of these three models. Okay? And there are some other reading materials. I think I heard this slide will be online or something. It will be shared with you guys, so you can just go home and take a look at this too. Okay? All right. Any other question? Is it okay to Ollie? And what is it again? Yeah. If you have any other question or you want to discuss anything, we can do that. I think the third lecture actually will be a little longer, but I don't want to start the third lecture now because I think it will be cut in the middle in a weird way. So I will try to just speak faster in the third lecture later. It's more high-level topic anyway, too. Okay?
Or shall we maybe start the third lecture 20 minutes earlier?
Yeah, I'm okay with that, as long as the organizer is okay, yeah. I don't know what's, yeah?
So if we start at 1:40 instead of starting at 2 o'clock? And then we go for lunch now. Then we have the same time for lunch.
Why don't we start at 1:50 then? Is it okay for everyone? Or is it okay to do it, Evan? I don't know. Yeah? Okay. I mean, let's just start at 1:50 unless anyone has constraint. Okay? All right? And if any question right now? Yeah.
Based on reinforced learnings, did you think about what kinds of the applications that is more suitable for us to use it?
Oh, what kind of
application? We can use the application in the real world,
right.
Or because it's you just to show lots of examples to learnings from the virtual world.
Right.
In the real world, do you
right.
think about, based on your research,
right.
this kind of algorithm is the most suitable
right.
what kind of task? Yeah.
Okay. So the question was, what kind of applications are there for reinforced learning? Practical reinforced applications, right? Other than just games. That's a good question. If you know the answer, let me know. But there are a few I know as well. One, I mean, obviously, just robotics applications in general. That's a basic, golden nugget for everyone right now. That's why I think in RL is being applied to many robotics problems. But that's rather obvious. And also, it's still very challenging for obvious reasons we discussed today, too. But there are a few other things, too. Because if you think about many applications, for example, question answering or text-based applications, too, it's very interactive, too. But many things the data is gained online, and you have to try and error to learn what is the right answer, what is the right way of approaching humans, and so on. And so people are applying reinforced learning algorithms to text-based, chatbot algorithms too, for example. So anything interactive, anything require interactive, and the data is gained online in an interactive way, and you have only one shot to try, and you never got a second chance kind of thing, then oftentimes people use RL-based approach now. But in the reality, right now, I don't think RL is being used as much as supervised learning algorithm, because I think supervised learning algorithm, people claim, and I also agree that once you have enough data, it's pretty much like solved problem. Solved problem. Whereas in RL, that's not the case. So it's hard to argue right now. But in general, anything interactive, anything you can imagine interactive, you can apply RL algorithms right now. Anything real time, in other words.
Yeah, so based on, you have the slides that shows that the robots that it can to be run by itself. So based on that text, the robot is just to learn how to detect the object or how to pick up the object.
Right.
What kinds of the test is this for this learning?
So the task was, it's a visual motor problem, which means you get this image input and you get the output, which is action. So you don't actually explicitly detect the object or anything like that, but rather you just get an image pixels, just like what I see right now, and then you take some action, and the goal is to pick up the objects or push the objects, etc. And this, the best labs doing this type of work is from Berkeley, Peter Abil and Sergey Levin, and they are produced a lot of good result on this so far. And now one of the students actually has moved to, I guess, MIT, but she didn't start the job yet. Yeah. Yes.
So my question is, in actual interaction with human,
yeah.
there are some irrationality in humanity. So
right.
How do RL deal with that since the reward might change?
I see. So in the question is, there is a lot of irrationality, and how do we model that, right? It's not really about RL anymore. It's just about the modeling, right? And if we treat deep learning algorithm as the sort of oracle, then implicitly should handle all this irrationality and then put them into account as well, implicitly as well. Explicitly, we don't do anything. I don't think I know any work trying to explicitly model irrationality or stochastic issue of the environment as much. But they just assume that can be handled by this estimator, like neural network functions. That's how it works also anywhere else too, right? In supervised learning, there's a lot of errors. Usually the data set we train from, usually people say there are at least 5% of errors or so, labeling errors. But that errors is just handled implicitly by neural networks too. And that's the same probably, so yeah. Yeah, the question is, it's not really about reinforcement. It's more about, should we explicitly model human or irrationality, or should we just implicitly hope that the model, any model, is either deep learning model or any other model can, learn it. So, yeah. Yes. So the question was, how do you know when to stop the exploration, right? So there's no like a real definition of exploration or exploitation, right? It's just parameters. Like we didn't talk about it in today's lecture. So there's a term where you decided whether to learn or explore essentially, or whether to exploit what you already know, and that's just a parameter also too. Or you can put it as a parameter. But in general, you never learn to explore. You keep exploring still. Meaning, exploring really just means that you just do random action in some sense, or some exploration means it doesn't follow what you think is best yet. But you never do. But sometimes people reduce the number of exploration, the chance of doing exploration versus exploitation, or sometimes people keep it as a constant value. But the more you learn, probably you are going to be more confident. So you will explore less and less, intuitively at least. And people put it as this is also ongoing work, and one of the way of what is the trade-off, and how do you actually trade off this correctly? Yeah. Okay. Any other question? Okay. Cool. Thank you. So, are we meeting at 1:50 then? Okay, then we will start at 1:50 then. I will see you guys. Thank you.